you love me, baby? Still you tell me maybe that someday when you say goodbye, yes, that'll be the day. When you make me cry, you say you're gonna leave. You know it's a lie, 'cause that'll be the day when I die.
Hey everyone, the roads here suck here, and I recently scored another free trial of SiriusXM. Yes, another, yes, free. The first time they gave me a free trial because I took my airbag to a dealership to have it replaced under a recall, and I guess the dealership gave me a trial. And this time I actually went to SiriusXM's website and just got a trial myself. So now that I had 2 free trials, I figured I might as well as give them a little bit of publicity for the free radio. Any case, I was driving around and there are these spots where there is always a lack of reception. The radio basically just always goes quiet, and it's always in the same exact spots. Now, SiriusXM basically has 2 satellites. So, forgive me, I don't know how to draw satellites, but let's just say this is a satellite with some sort of radio dish. Here are some solar panels, right? Look at that. It's actually not that bad, I suppose, but here's a satellite. They have 2 of these, and what they do is they basically stream along, well, broadcast along the 2.3 gigahertz range. So that's in the ultra high frequency band, if I'm not mistaken, which is pretty much line of sight. Whatever is going to be receiving these signals has to have direct line of sight with the satellite. So if there's an obstruction, like let's say, I don't know, Eiffel Tower the size of something, I don't know. If there's an obstruction, then basically you have no signal. So when you're driving in your car along on the highway, again, crap drawing of a car, but let's just say you're driving along a highway and you have one of those receivers on the back of it, you are getting signal from the satellite until you basically drive under a bridge. I'll try to keep the paper here with the camera, there we go. So when you go under a bridge or by a building or something along those lines, that is basically blocked off, resulting in a loss of signal. And the fact that this happens in the exact same spot every single day basically means that these satellites are in geostationary orbit. They have to be. So SiriusXM basically works on 2 principles. You have satellites in the air. Let me actually do this. Oh, that's much better. You have satellites in the air, and if you're in a big metropolis, I don't know, let's just say there are buildings here. If you're in a big metropolis, they will either broadcast directly to your car, or if you're in a big city like Manhattan, they will broadcast to basically a repeater, which then broadcasts it to your car. But again, these are only in big cities. So when you're out in the middle of nowhere, all you basically have is this little receiver on your car and direct line of sight with the satellite. So only direct line of sight with the car. And as I was saying, for lack of signal to be happening in the same exact place each and every time, the satellites have to be in geostationary orbit. Take note, geostationary is not the same as geosynchronous. Geosynchronous basically means that the satellites complete an orbit at the same time that the Earth makes a rotation. So if here's the Earth, the satellites would orbit, I don't know, in something like a figure 8 type of thing. Whereas geostationary orbit is basically, worst drawing of the Earth ever, but if the Earth rotates this way and the satellite orbits this way, and if the satellite is here, that means the satellite is orbiting exactly at the same speed as the Earth is rotating, so that it is always facing one point on the planet. So, SiriusXM has satellites. These satellites have direct contact with, or direct line of sight with cars. And these satellites are in geostationary orbit. Otherwise, the phenomenon that I've been describing would not be happening. Now, here is our planet, and it is spherical. This will be the equator, and the average distance from the center of the Earth to the surface of the equator is 6,378 kilometers. Now, the Earth itself rotates once every 23 hours, 56 minutes, 4.1 seconds. Now, let's just take this and I'll make it 1 unit of time, which would be seconds. So we have 23 hours, and there are going to be 60 minutes in 1 hour, and there are 60 seconds to 1 minute, which basically works out to be 23 hours times 60 minutes times 60 seconds is going to give us unit of hour minutes. Minutes cancel, hours cancel, and we are basically left with 23 times 60 times 60 is equivalent to 82,800 seconds. That's the 23 hours. Now we do the 56 minutes. So 56 times 60 is going to be 3,360 seconds. And then 4.1 seconds is just 4.1 seconds. Altogether, this totals out to be, let's see, 82,800 plus 360, there we go, plus 4.1, like so, 86,164.1 seconds. So 86,164.1 seconds is one full rotation of the Earth about its axis. Now, for a satellite to be in geostationary orbit, it has to face one point of the planet consistently. So that means the satellite's orbit is the same as the rotation of the Earth. Or I should say, the period of the satellite's orbit matches with the period of the Earth's rotation, so that the satellite can always be facing one point on the planet. And the satellite also has to be on the equator. The equation for period is, the period is equivalent to 2 pi times the semi-major axis to the power of 3 over 2 over mu to the power of 1/2. The semi-major axis is basically the radius of the Earth, because the Earth is spherical. And mu is basically, I forget, I think it's something like the specific gravity constant or something, but in any case, it's the gravitational constant times the mass of the body. In this case, the Earth. This happens to be equal to 3.986 times 10 to the 5 kilometers cubed per second squared. Anyways, we have our period of 86,164.1 seconds, which is going to be equal to 2 pi times the semi-major axis, or the radius, to the power of 3/2 over 3.986 times 10 to the 5 to the power of 1/2. Now, we need to solve for A. So, rearranging these things, it's going to be 86,164.1 seconds times 3.986 times 10 to the 5 to the power of 1/2 over 2 pi is equal to a to the power of 3/2. 3/2. Let's simplify this a little bit now. We have 3.886.164.1 times 3.986 times 10 to the power of 5 to the power of 1/2, which basically comes out to be like this. We get that number over 2pi, which gives us this number, which is 8,657,951.226. So let me just jot this down. 8,657,951.226 is equivalent to the semi-major axis over 3/2. Now, doing a little bit of the algebra thing, we're just going to solve for A. So we have basically this answer to the power of 2/3 is equivalent to a 3/2 to the power of 2/3, which will just give us A, which is, so we take the answer, which is the second answer, right? Answer to the power of 2/3, which gives us 42,164.15715 kilometers. Remember, this is from the center of the Earth. So, deducting the distance from the center of the Earth to the surface of the Earth at the equator, we're basically going to get 42,164.15715 minus 6,378 kilometers, which will be 35,786.15715 kilometers. Note that this value is approximate because we used an approximate value for the equator. It's not consistent throughout the entire planet. You know, some places are 6,371 kilometers, some places are a bit more, some places are a bit less, so on, but average value should be very close. So, using the radio from my car, we experienced behavior which demonstrates that the satellite is in geostationary orbit. And for the satellite to be in geostationary orbit, it has to be around the equator at this altitude. Now, SiriusXM has two satellites. They have FM5 and FM6. Again, transmitting, excuse me, transmitting along the 2.3 gigahertz band, or the ultra high frequency band, which means it needs direct line of sight. Anyways, there's a website that tracks these things. It's called Stuff in Space. So let's just do this. Right. This is a thing that tracks all of these satellites. And let's look up FM5. All right, FM5 is at the equator. It's this green little dot. Let's see if I could just move it around here. Oh, without messing things up. Jeez. Okay, yeah, so it's orbiting the equator. And the apogee is 35,798 kilometers. So this is the furthest from the Earth that it gets. The perigee is 35,790 kilometers, which is the closest to the Earth it gets. And the inclination is 0.03 degrees. The inclination is basically the tilt of the orbit. They couldn't get it exactly perfectly spot on with the equator, so that's why there's some fluctuation in there. Let's see, but the current altitude above ground level is 35,781.63 kilometers. Let's check that with our answer of 35,786.157 kilometers right here. So we're only about 5 kilometers off. which is not bad considering we use the average value for the radius of the Earth. Now let's check their other satellite, FM6, which is also in geostationary orbit. And it's right there. So basically you have one for the west coast of the United States and one for the east coast of the United States. And the altitude here, again, is 35,790.91 kilometers because it has an inclination of 0.02 degrees. So we are about 4 kilometers off with our estimation there. But, so let's say we take a look at the sat beams for these satellites. This is what it is for FM6, for example. Right, exactly. So from this point, which is along the west coast of the United States, it is transmitting basically to here. And what if we checked FM5? And this would be FM5. For the East Coast now. There you go. So you have these two satellites working in tandem with each other. They are in geostationary orbit, but every now and then there will be an obstruction with the direct line of sight of these satellites. And that's why we have the lack of signal at those exact spaces consistently and always. Now you might ask, how does this prove that the Earth is in fact round? Well, the real life situation we encounter matches up with the technology used, which matches up with the mathematical explanation for why this stuff happens. If you wanted to prove that the Earth is flat, what you would have to do is you have to tell me what would be geostationary orbit, and that's not going to be an easy thing to do because if the Earth is flat, where's the center of the Earth? And if the Earth rotates, you know, you're going to have different accelerations or velocities throughout this rotation the further out you go. Angular velocity or something, blah, 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 blah. Which means that if you want to put a satellite in geosync orbit so that the SiriusXM exhibits that kind of behavior, you're going to have a hard time mathematically proving that, if that makes sense. So there you have it. So, quick recap. There is a phenomenon that has been occurring that I have captured on Dashcam that can only be explained given a certain technology, under certain conditions. And if the Earth is spherical, these would be the parameters of all of that stuff, which gives us data that is consistent with what tracking for these objects shows. Does that make sense? So this proves that the Earth is round, spherical, that is. Now, let me give you a little bit of a bonus to further drive this point home. We said the altitude is, let's just say, 35,786.2 kilometers. So 35,786.2. is the altitude above ground level. So let's just add 6,378 kilometers again to get that distance to the center of the Earth again. That is going to be 35,786.2 plus 6,378. We get 42,164.2, and we know that the equation for orbital velocity orbital, is equal to the square root of mu over r, which is equal to the square root of 3.986 times 10 to the 5th over this radius, 42164.2. Let me crunch some numbers. We have 3.9, let's clear that and do it over. 3.986 times 10 to the 5 over 42164.2, which gives us this. Let's take the square root of that answer, which gives us a velocity of 3.0746 blah 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 kilometers per second. And now let's see what the data shows for FM6. 3.07 kilometers per second. There you go. You want to see? Let's check FM5 right here. FM5, please. 3.08 kilometers per second. So again, mathematically, this is golden. If you want to make a case for the Earth being flat, what you would have to do is, let's say you have a disc-shaped Earth, right? This is a disc, not a sphere or anything. Disc-shaped Earth with a center rotating a certain speed or traveling a certain speed. I'm not sure how the whole flat Earth thing works with orbital mechanics and all that stuff, but you have to remember that each point is going to be going around at a different acceleration, velocity, so on. And this technology and this phenomenon means that the satellite has to be in geostationary orbit such that it faces everything and travels at the same speed as everything else around this planet. All right? So if you can mathematically show me the speed, the distance, and let's see, and what else? Speed, the distance, and of course this thing is going to have a height to it too, because this isn't, because the bridge isn't a two-dimensional object, the car isn't a two-dimensional object, so on. So there has to be an angle here. If you can find a way to mathematically prove all of this such that this thing will have the altitude that is being observed from Earth and the speed that is being observed from Earth, then you can make a solid case for the Earth being flat. So there you go. Proving the Earth is spherical using a Dashcam, SiriusXM, and a little bit of orbital mechanics. I hope you enjoyed. Take care and have a nice day.